All right, this week it's about the conservation of momentum. Last week we learned about impulse and momentum. Impulse causes a change in momentum. It's how you gain or lose momentum. Before that, we learned about how work causes things to gain energy or lose energy. Work is a force times displacement, but impulse is a force times time. Well, today we're going to carry that a little bit further with the law of conservation of momentum, and also look how that compares to the law of conservation of energy as well. Okay? So first of all, remember momentum is mass and velocity. So to make anything gain momentum, to accelerate it, you have to have some kind of a force applied, some kind of an unbalanced force, and it has to be over some period of time. Because that force over a period of time is the impulse. Remember, force is an impact, but an impulse is a force over a period of time, and it must come from outside the object. It's not an internal force, it's an external force. An example like air in a basketball doesn't cause a ball to do anything. Or somebody inside a car, you can't make it go forward or backwards by jumping around in the car. Sure, you can be in the back seat and jump forward, which initially causes the car to go back a little, but as soon as you hit the front seat, it's going to push the car back towards the front, and there's really no change. So those are all internal forces. Or you sit in a boat, you can jiggle around, but you really don't make it go anywhere. So we need an external force to make this impulse to cause a change in momentum. So internal forces are balanced and they cancel each other out, but external forces are from the outside of that car, like the wheel pushes road, road pushes wheel. So if no outside force is present, there's no change in momentum. Can't happen. That's a law of conservation of momentum. So the only way to have a change in momentum is have a net external force acting on it for a period of time. Okay? So law of conservation of momentum. Here we go. So if you don't have an external force acting on it, there's going to be no change in momentum. External forces tend to be things like friction. So if you, there was something. There is a huge explosion. But for example, in your car, if you turn your car off, you're going down the road, you'll slow down because you have external forces of 1, air drag in your car, and 2, friction acting on it to cause the thing to slow down. If you didn't have any friction or air drag, your car would stay at the same speed the whole time, not change momentum unless you had an external force on it. So the big kaboom a moment ago, that was we'll try that one more time maybe. That was a star going kaboomy. How much momentum does a star have? It doesn't have any momentum, but as it blows up like that, you have pieces going left, pieces going right, pieces going up, down, in all directions. Every one of those pieces adds together is going to sum up, since momentum is a vector, it's going to sum up to 0. So the kabooming of a star, that's a net internal force. It's not really a change in momentum of the thing. Okay? So we're looking at forces that are outside of a system that causes a change in momentum. Okay? So remember, this stuff is all a takeoff of Newton's laws of motion. Okay? Just another, carrying Newton's laws of motion a little bit further, it's really based off Newton's laws of motion. So this is the FMA thing. Okay? So if there's no net force, is there no acceleration? Well, of course there's no acceleration if you don't have a net force. It doesn't change motion. So you can't have a change in momentum either. Forces on a cannon are equal and opposite. Does it follow that the impulse exerted on a cannonball are also equal and opposite? Well, if you have an equal and opposite force, and the time that the cannon pushes on the ball is the same the ball pushes back on the cannon, yes, they both have to have equal and opposite impulses acting on each other. Okay? Because that's both the same, the force and the time. Alrighty, so if you don't have any external impulses on something, whatever momentum you have beforehand has to be the same momentum as what you have after the fact. Okay? So this holds true for all systems. Alrighty, so we've got a collision between a couple things. Okay? Here's what elastic collision is. Elastic means that we keep the same kinetic energy before and after the collision. So if these two balls are exactly the same mass, now one ball is going to hit the other, but we're saying there's no friction involved. So if we don't have any friction involved, and this is our system, both balls together are system, sure, red ball hits white ball, and white ball hits red ball just as hard, but if we call this the whole system, both balls together, that's actually an internal force. Meaning whatever momentum we have inside this system before has to be the same as afterwards. Does So any predictions what happens if these two balls are the same mass, one ball rolls in and smacks the other? Well, you have to have the same momentum before and afterwards. If we don't have any external force, we're calling that smack an internal force. So to have the same momentum, if this ball stops, that means your second ball, just like in pool, tends to go off at the same speed. And that means not only is momentum conserved, but so is your kinetic energy. Remember, momentum's m times v, kinetic energy is 1/2 mv squared. Okay? So not only do we have the momentum conserved, but we have the kinetic energy conserved. Now in real life, you don't quite have a perfect elastic collision between balls because you hear a smack. That smack takes energy. You're vibrating air particles, and that vibration spreads out through the air. And so we're losing some of your energy into the smacking of it. So in reality, the kinetic energy is a teeny bit less as this ball rolls on and so forth. But in theory, there's pretty close to the same kinetic energy, so we tend to call that an example of elastic collision, when in reality, these elastic collisions only happen between subatomic particles. Okay, so that's a mostly elastic collision defined by have the same, not just momentum, but kinetic energy afterwards. Okay? All right, oh, head on, bam, okay. Now in this particular one, let's back that up a little bit. So let's say both balls have the same mass and the same velocity. So if this is part of our system, both balls, when they smack, we're going to call that an internal force, meaning whatever momentum you have before, you have to have afterwards. Now it turns out, what do you think would happen if one ball was maybe more massive than the other? Well, they're not going to shake. That was an example if they're pretty much the same mass. Well, something different happens, but if it's an elastic collision, you still have to have the same momentum and kinetic energy after the fact. But if they are indeed the same mass and they're going the same velocity, they will go backwards at the same velocity they came in at, if they had the same mass and velocity starting out. Alrighty, so it looks like we have another example here, and they're both moving, and what happens? So once again, this is still elastic because this is going to be an internal force. Sure, this one gains speed because we did some work on it, gained some kinetic energy, but we had some negative work on this to slow it down. But if it's indeed an elastic collision, you still have the same total kinetic energy before and afterwards. Meaning the one that slowed down has less energy, but the one that sped up has more energy, and it also has more momentum. Okay? So that's an example of elastic collision. You have both the same momentum and kinetic energy afterwards. And you might say, hey, what if you hit not exactly center on? Well, if you don't hit exactly center on, and that one wasn't quite center on if you watch, one ball will go this way, one ball goes this way, they still have the same kinetic energy and the same momentum if it's indeed an elastic collision. They're going to pretend that this is a straight on one, even though it's not quite a straight on one. Oh well. So, inelastic. So what's different about inelastic collisions? Well, we're still going to conserve momentum, but we're not conserving kinetic energy. So when you ever have an inelastic collision, kinetic energy will not be conserved. Oh, here we go. We've got a couple carts that are going to ram together. This will be fun, Okay, so pop quiz. Let's go back a little bit. Oh, now it's forwards. We're going backwards. Which one of these two carts had more mass? Okay, why would you think the red one has more mass? Well, if they're going about the same speed and the net momentum was to the right, well, that has to mean that the total momentum before the collision was also to the right. So in other words, we don't really know what the masses are, but they look like they're going about the same velocity. So if it's a total complete inelastic collision, they have indeed the same mass and they have the same momentum coming towards each other, the same momentum. If it's elastic, they would bounce off like we saw the balls. But if it's not elastic, if it's inelastic, perfectly elastic, that means they stick. Whenever you hear the word perfectly inelastic, that means they stick. Now, if they had the same momentum, that would mean this momentum plus this momentum is the same amount, but one's negative. That means you really have no net momentum if the whole thing is your system. If we count the whole thing as your system, these crashing together are internal forces. And so the positive momentum plus the negative momentums would sum to zero if they had the same momentum. But as we can see from this, the momentum afterwards is to the right. That means you have to have more momentum in the right direction before they even hit. Which, if they're going the same speed, that means the red car was more massive, so you had more momentum to the right to begin with, and you have the exact same momentum afterwards. Even if it's inelastic, you still have to have the same momentum, the vector momentum. Remember, one's negative, same vector momentum before and afterwards, but you will not have the same kinetic energy, as you lose some energy in the smacking of things together. Okay, got a few minutes left here. So you may have seen something like Newton's cradle. Maybe I'll try to take that home. I'm going to go up to school tomorrow. Maybe I'll grab it and I can do a video with it. We'll see. But one ball comes in, one ball leaves. The reason this happens is because it's a inelastic or elastic collision. What we're going to find out in this case is going to be an elastic collision. That's not exactly what happens. This ball's coming up and so on. But we're going to learn, and hopefully I'll bring that home tomorrow and do another video, and we'll talk about why it's elastic or how to make that thing elastic. But if it is elastic, that means whatever kinetic energy you have coming in is also leaving over there. Okay? So we'll do a little more on that hopefully tomorrow if I can get that home. Alrighty. Here's a problem. Again, I love the fish. We might actually just pause the video here and do some problem solving, so it's all together with the fishies, and we'll talk about, is this elastic or inelastic collision. Alrighty, taking a break.